Hey there. So we left off. I don't know, where did we leave off? Somewhere towards the end of generics. Um, I do believe. All right, and we have a problem. The problem. Associated items. Let's go back. What is associated items? Associated items refers to a set of rules pertaining to items of various types. An extension to trait generics allows traits to internally define new items. Yay. I don't think. No. Did we go that far? Where clauses? Yeah, we did where. We did this. Right. We did this. Yeah, so this is where we left off. So it's an extension to trait generics that allows traits to internally define new items. Okay. One such item is called an associated type, providing a simpler usage patterns when the trait is generic over its container type. That's a bunch of words that don't mean a whole lot to me right now. All right, let's see if they can explain it a little better. A trait that is generic over its container type. Generic over its container type. I'm sure that's going to mean something to me in the future. Has type specification requirements. Users of a trait must specify all of its generic types. Okay. In the example below, the contains trait allows the user the use of the generic types A and B. The trait is then implemented for the container type, specifying I32 for A and B, so that it can be used with difference. Okay, let's just see, what is he talking about here? So we have contains and A and B, and we're saying, okay, this one explicitly requires A and B. This one does not explicitly contain A or B. A trait which checks if two items are stored inside a container also retrieves first and last value. Okay, it contains. All right, sure, I guess. And then we implement contains I32 for container. True if the numbers stored are equal. Grab the first number, grab the last number. Okay. All right. Okay, so here we've got our definition of a trait, a generic thing. So we're going to say, okay, this is a whatever contains thing, and it's going to have these functions. It's going to have to implement these functions. Contains first and last. And then we've got an int32 implementation, or I32 implementation, where we implement those three things. And then difference ABC, container C, returns I32. So C contains A and B. In light of that, having to express A and B again is a nuisance. Okay. I'll take your word for it. Oh, wait a minute. What do you mean? Where C contains AB. Oh, okay. So I think the syntax was a little wordier here. Is that what you're trying to tell me? Is that, hey, we can do this without such wordy syntax? Okay, fine, whatever. And then we can do container 1 and 2. Container.contains number 1 and 2. And we use the ampersand because we're borrowing those. And container.contains. Container first, container last. The difference is container. Difference passing in container. Okay. All right. Okay. Okay. Not particularly meaningful to me right now, but sure. Associated types. The use of associated types improves the overall readability of code by moving inner types locally into the trait as output types. This is just like without using the associated types, where we would have to say contains AB, and difference contains container C. Okay, let's rewrite the example from the previous section using associated types. Oh, okay. So now I finally understand. Okay, so this is a nuisance. It wasn't that much of a nuisance to have to write A and B again. Like, seriously, man. It wasn't that bad. Maybe it gets really bad later, but okay. So then with associated types, we can say trait contains type A, B contains self B, self A. Okay, so how's this? Let's have a look at, so compare that. Trait contains type A, type B, self A, self B, bool. Okay, so let's go back to the original one. And this one says contains, trait contains AB, contains self A, B. Okay, so the difference here was there was a type A, type B thing here. And then this is self A, self B. So this got wordier because it's ampersand self A, ampersand self B, A and B. But this is simpler because this contains does not have angle bracket ABC. Okay. Because it's just got, so this AB is missing because we define the type inside. But then this became wordier because we had to say, oh yeah, it's not just AB, it's self A and self B. Right? Self A and self B. And it's capital S self B and A rather than lowercase s self. And how the heck am I supposed to remember the difference between lowercase s self and uppercase s self? I don't know. Note that functions use a trait contains no longer require express A or B at all. So without using the associated types ABC, okay, where contains AB. Oh, got the yawns all of a sudden. Associated types, difference, C contains, container C, blah, blah, blah. Okay, so then we've got contains AB, self, self, self. Oh, these selves, are they the same selves? Well, yeah, they're the same selves. Yep, they're the same selves. Okay, this is what's added. That was added. The angle, the generic angle bracket ABC thing was, AB thing was removed. Okay. And here, this is how we're going to specify that this particular one deals with integers. And then here, right, I32, grab the first number, grab the last number. Okay, and then difference. Now, does this one look any different? Contains the difference. ABC. So, okay, I see it's like, hey, so if there's a lot of them, then that would be a real pain. A, B, C, D, E, F, G. Contains A, B, you know. So, because we can use the type. And then we don't have to keep specifying them over and over again. We just need to specify the final thing, the contain, the C. Okay. All right. And then over here, it behaves pretty much the same way. Cool. I guess. All right. Phantom type parameters. Phantom type parameter is one that doesn't show up at runtime but is checked statically and only at compile time. Data types can use extra generic type parameters to act as markers or perform type checking at compile time. These extra parameters hold no storage values and have no runtime behavior. Good Lord. Why? Phantom data B. Phantom data struct. Okay. Okay. Can't use B for computations. Sorry about that. I don't know. The bright lights have just suddenly made me yawn. Okay, so phantom data. Oh, this is really weird. So here are hidden parameters, tuple, phantom tuple type specified as. Alright, what the heck? Phantom struct, phantom data, phantom data. Why? Alright, okay. Compile time error. Type mismatch. These cannot be compared. Tuple. Because this is an F32 and this is an F64. So if we try to compare them, we won't be able to, even though the stuff we actually work with. So that I guess that's a way of distinguishing between two structures that would otherwise look identical, is to create some phantom data that was going to allow the compiler to go, no, they're not the same. Fair enough. Test case, unit clarification. A useful method of unit conversions can be examined by implementing add with a phantom type parameter. Okay, add. Okay. TU, so that TU plus TU equals TU. Oh dear. What are you trying to tell me? Oh. So phantom data unit. So if you have something of a length, but okay, we add two lengths together. 1 meter, 1 foot. Oh, because inch and millimeters. Okay. So we won't be able to add 1 foot plus 1 meter together because the phantom data is different. Where did we define inch and millimeter? Where did he define inch? Oh, here. Enum inch, enum millimeter. Oh, okay. So void enumerations. So an enumeration, so it's got a name. Enum's got a name, but no body to it. Oh, that's kind of cool. Okay, all right. Fair enough. This is a compile time way of saying, yeah, we can't add those lengths together because they're different units. Okay. Cool. All right. Lovely. Just lovely. Okay. Scoping rules. Scopes play. Yeah, we saw this already. Scopes and who owns what and lifetimes and borrowing. Okay, so there's some rules here. Variables in Rust do more than just hold data in the stack. They also own resources. Box T owns memory in the heap. Rust enforces resource acquisition is initialization. So whenever an object goes out of scope, its destructor is called and its owned resources are freed. This behavior shields against resource leak bugs, so you'll never have to manually free memory or worry about memory leaks again. Very nice. Oh, that's interesting. So there is a destructor. So I guess, but there's no garbage collector, as I understand it. So then the memory is freed like you would normally free memory in a C program, like when you're done using it, except that I guess this is going to take care of doing that on our behalf. Okay, so create box, allocate an integer on the heap, allocate an integer on the heap, allocate an integer on the heap. Box 3 is destroyed here, and memory gets freed. Create lots of boxes just for fun. There is no need to manually free memory. Okay, because this create box is going to create a whole bunch of boxes, but it's going to destroy them immediately because this doesn't actually return. Okay, we can double check for memory errors using valgrind. Rust, whatever, valgrind. Use that exit 0 and 0. Oh, okay. All heap blocks are freed. No leaks are possible. Oh, valgrind.ry. Okay. Actually, let's give that a try. That's kind of cool. So we've got this program. What's this called? Okay. Oops. What the? Terminal. New terminal, I guess. Generic trait. We have, okay. Change directory source. We have main. Do we not have, Rust C. Main.rs. Okay, there we have a main.exe. So we can say main or /main. And then what do we do here? And valgrind. Oh no, we do valgrind /main. No, valgrind. The term valgrind does not recognize the name of command. Well, all right. Is I'm spelling it wrong? Valgrind. Interesting. The term valgrind is not recognized. All right, let's try it. /. No, but that's not going to do it. All right. Let's go to here. Oops. Didn't mean to do that one. Let's go here. Let's add this. Rust C valgrind not found. Okay. Rust not entirely memory safe. Let's make this bigger. Well, okay, fine, but can we, how about just oh, okay, what's this? Cargo valgrind. Oh. This command extends cargo with the capability to directly run valgrind on any crate executable. This command should not be necessary for ordinary Rust programs. Okay. So what do we got here? Cargo valgrind run. need to have Valgrind installed. Okay, so I don't have Valgrind installed. So how do I install Valgrind? Valgrind. Okay, here we go. A small library of data structures. No, that's what? Cargo add Valgrind? Run the following cargo command in your project directory. Cargo add Valgrind. That seems weird. Alright, let's try that. Let's try the cargo add Valgrind thing and see if that does it. Cargo add Valgrind. Oh, it is doing it. Doing something. Well, this is the first time we've done this. Alright. Okay, adding Valgrind. Okay, so let's go Valgrind. It still says it can't find it. Unless they really meant it when it said, where'd it go? That we needed to do the Rust C, this whole thing. All right, let's do that. Let's do this. Let's do the whole thing exactly the way they say it. Rust C main dot rs and then valgrind dot slash main. Token end is not a valid statement separator in this version. Okay. What? Huh. What the heck's going on here? Okay. But so it's called Valgrind, but then it says memcheck, a memory error detector. What? Valgrind. Okay, let's click on this. Open link in new tab. Valgrind. Oh, okay. Okay, blah blah, lots of blah blah. Is there installation instructions, source code documentation? Documentation, quick start guide. Okay, introduction. Running your program, normally you run your program, use this command line. Oh, this is different. But Valgrind, introduction. Okay. Like seriously, people, where is the installation instructions? Like fine, the quick start guide, but installing. Like, come on, man. This is one thing I do like about JavaScript and NPM. You go there and it's perfectly clear how to install something. Every package has installation instructions front and center. No figuring it out. This, unfortunately, is painful, it would appear. Table of contents. User manual. What do you think? User manual? Getting started? No. No installation. Like, come on. Alright, let me try this. How do I install Valgrind on Windows? How to build and run Valgrind? I don't want to do that. How to install here? How to use it through the binary? Oh, look. Valgrind is a famous tool. Sadly, it only supports Linux. Okay, now I understand. It's easy since the new update. Windows has Ubuntu, sure. So we can't do it, or at least I can't do it, because I need to turn on. Okay. Windows substitutes for Linux after a restart. Download, install. Afterwards. Okay. So that's how to install Linux for Windows. But how about installing... Oh, here we go. Sudo apt-get install Valgrind. Okay. Oh, yeah, I just love it. Have to install and build it yourself. I guess it's not terrible, but okay. Well, forget it. I'm not gonna spend time figuring that out, but just make the assumption that we know. Okay, fine. Oh yeah, and destructors. Oh, drop. Implement drop. Destructor is called when the resource goes out of scope. The trait is not required to be implemented for every type, only implemented if your type requires your own destructor logic. Okay, so if you've got some external resource or a connection, maybe, that you want to, like a TCP/IP or a serial port or something, you want to close it off, we do drop, our own drop. Okay, cool. Ownership and moves. Okay, so here we go. So this has been the kind of the crux of the whole mystery, is this ampersand for borrowing and all this stuff. Maybe now we're finally going to get to the point where it explains what the heck is going on. All right. Because variables are in charge of freeing their own resources, resources can only have one owner. This also prevents resources from being freed more than once. Also a big problem. Note that not all variables own resources. When doing assignments, let x equals y, or passing functions arguments by value, the ownership of the resources is transferred. In Rust speak, this is known as a move. Okay, so this is different. This is like totally different, because in C# or Java, for example, or C# and Java, when you call foo x like that, it's making, and if x is like an integer, then it makes a copy of x, and it passes, and so then when you modify the x, like the integer x, in the caller in foo, it does not affect x in the main line. But this is saying that no, in fact, it's passing the ownership of x down to foo, and now foo won't return it back. There's no obvious path for foo to return it, the ownership. So basically it gets destroyed. And we've seen that in a bunch of the stuff we've worked with, right? Where you pass it in and it never comes back out. It just vanishes. And you take advantage of that as, like, if I want to destroy something, I pass it in somewhere. And it moves it into the somewhere, and when the control is lost, or the scope is out of, when the scope is closed, or whatever, how we're going to say that, the variable is gone. Okay. So this is like the syntax is the same, but it means a totally different thing. So now y no longer owns it when that x equals y. The ownership is transferred. So y no longer owns the data, x owns it. Hang on a second. I'm just looking at here. No resources are moved with this. So what? But you just said ownership of the resources transferred. No, this is known as a move. But this says no resources are moved on the same. What are you doing? Like, seriously, you said right here that ownership is transferred. And then here in the code you say, nah, we didn't. We made a copy. Which is, that's the normal thing, is to make a copy. When you do, x, you would say let y equals x, you make a copy. And both are independent. Yeah, that's kind of the expectation. Like, that's how other C-like languages work. You're scaring me there by saying we've moved. But we did see that when you make a call, that it does move. Okay. A is a pointer to a heap allocated integer. Okay, box new 5. So, contains 5. I see. A stack allocated integer makes a copy. A heap allocated integer does a move. So here, the pointer address of A is copied into B. Both are now pointers to this same heap allocated data, but B now owns it. Okay, so error, A can no longer access the data because it no longer owns it. So there we go. There's the owner transfer. Okay, this function takes ownership of the heap allocated memory from B. Destroy box B. Right. So destroy box, basically we pass in the box and don't do anything with it except maybe print out debug statement, and it's gone. Okay. All right. I get it. I get the box thing now. So box is heap. The plain thing is stack. And so stack allocated things only take up the 4 bytes. Like in this case, the int32, the 4 bytes that an int32 takes up. And so it's pretty easy to make that copy. But, all right. So now what if we did this with, now are you going to do this? Are you going to do this, or shall I do it? Because fine, that makes sense for integers. But what about strings? So integers, floating point numbers, those kind of basic things. Where the boundary is different, right, is strings. Because strings are weird because they're arrays, so they're like some crazy length potentially. But I believe they're still allocated on the stack. Arrays are allocated on the stack. If I remember correctly, right, when we were talking about arrays, they were allocated on the stack. All right, so let's pop over here. All right, we're going to give up on that. What we are going to do is, so if I do something like, so let's borrow the code here. So we had, all right, let x equals 5i32. Let y equals x. And then if we do a print line x, y, x, y. All right, and if we run this, there we go. X is 5, y is 5. Okay, yeah, because so that makes sense. That makes sense. Now, if I change this, so let's do it. Let's repeat this, but let's do the box thing. All right, so now this is going to be, what was the syntax? Sorry, I'm gonna have to go look again. This guy. Box : new, that. Okay. Whoops. Where are you? There you are. Box : new. Okay. All right. Oh, and now it's complaining about x. It says, right. So now we've got that error that we kept seeing over and over again. Move occurs because x has type box, which does not implement the copy trait. Right, so this does a copy. That's what they were talking about. This does a copy. You cannot copy this. Okay. Fair enough. And so x no longer owns it. Borrow of moved value x. Value borrowed here after move. Okay. So what if I did an ampersand? Because I'm borrowing. Okay. So that actually, so now let me run this. Let's see if it works. Run. 5, 5. Okay, so if I borrow x and copy that, so it looks like it's still doing a copy now because, right? Is that a bar? Oh, no, no, no. It's a borrow of x. So, all right. So x is the owner. X continues to be the owner, I'm guessing. And y is the borrower. And so both the owner and the borrower can both have access. Okay. But that means then that, yeah. So there's still only one owner. And when the owner goes out of scope, the thing goes away, I would assume. But what if you, we'll find that out another time, I guess. What if you borrow something and, pass the borrowed value along? Oh, I guess you can't really do that because as soon as the borrower goes out of scope, it's going to be, yeah. So no, you have to do a move if you want somebody else to have ownership and for the lifetime to extend past. So if we wanted the lifetime to extend past the function we're in, we'd have to pass it somewhere where the owner would not be destroyed. Obviously we can't do that in main because main is our main guy. But yeah. Okay, anyway. Now the question was strings. So so here's the thing, right? So x equals the rain. let y equal x. Okay. So it's ampersand stir. So it's a borrow. So it's already a borrow. So if I say print line, actually let me just, I can just copy this. Okay, so it's still happy here because this was a borrow. So if I say box colon colon new the rain, okay. Well, that's weird because this is, it's still happy, I think. Oh no, it's not happy because the ownership of the box ampersand stir got passed to x, right? And I can still say ampersand x and then it's happy again. Okay. All right. I see that happening. All right, and can I build this? Nope. Value borrowed here after move. Okay, so it's going to give me that. It's not going to let me build the code. Fair enough. All right. So strings behave the same way as basic values, although the string is not a string, it's an ampersand stir. So it's initially borrowed, I guess. It was that would be that syntax. All right. Well, let's move on and see what it says. All right. We've covered all of that. Mutability can be changed when ownership is transferred. Okay. Immutable box. So we have an immutable box. Oh, and star immutable box equals 4. Oh. So if I get it now. The star, because this is on the heap, this is a pointer. Now I understand. So, okay, so then this, because it was in a box, we need to use star to access the contents of the box. And it's not mutable, so we're going to get this error. If we move it into mutable box, the mutable box, then when we go to make the change, it works because now this new owner is mutable. Okay. That makes sense. Partial moves. Yeah, because why not? With destructuring of a single variable, both by move and by reference pattern bindings can be used. Wait a minute. You've introduced two new pieces of syntax, by move and by reference. Pattern bindings can be used at the same time. Okay, let's find out if they explain what that is. Doing this will result in a partial move of the variable, which means that the parts of the variable will be moved while other parts stay. Seriously? Okay. So we've got a person who has a string, a capital S string, and a box with a U8 in it. String from Alice. Ooh. Okay, and then age box is new. And then the name is moved out, but age is referenced. Name is moved, but we do a ref age person. The person's age is, the name is. We can't display it person, but we can display the age. Okay. Right, because we're referring to age, but we moved name over here. Okay, what I want to do, I want to try this. Because I did ampersand stir. So what if we did, so let's get rid of, this would be string, capital S string, from, was that what it was? From, yeah, from, just from. Okay. Oops. So what's the type? So this is a capital S string. Well, that's interesting. All right, let's control S. Yeah, well, we're complaining. It's complaining again. Because here we string from, so it's a string, capital S string. Alloc string. The string type is the most common string type that has ownership over the contents of the string. It has a close relationship with its borrowed counterpart, the primitive string. You can get a string from a literal string with string from. Okay. Okay. UTF-8, all that good stuff. Okay, fine. So I don't know, which do we want to use? Do we want to use that primitive ampersand stir, or do we want to use capital S string? Looks like we can do more stuff with capital S string because there was that whole business of appending. So it's like a string buffer. We can get a length and as bytes, and so string implements deref target stir, so it inherits all of stir's methods. In addition, it means that you can pass a string to a function that takes an ampersand stir by using an ampersand. Oh, okay. String from hello, pass that in, okay. This will create a stir from the string and pass it in. This conversion is very inexpensive. In the following example, a string slice implements the trait example. We still haven't figured out what this quote A thing is. Or kind of we did. I don't remember it though. Here we go. A string is made up of three components: a pointer, some bytes, a length, and a capacity. Okay. The buffer is always stored on the heap. Gotcha. So this is heap storage. I'm assuming ampersand stir is stack. I don't know if that might be a good assumption, maybe not. Okay, and then it expands capacity. Oh, cool. Okay. Lovely. All right. But so this is stack. This is heap. This is stack, would be my guess. All right, back to the explanation. All right, there you are. Okay, partial moves. This is weird, but sure, why not? So I borrowed age, but and using the ref keyword, but I moved name. Okay, borrowing. Most of the time, we'd like to access data without taking ownership over it. To accomplish this, Rust uses the borrowing mechanism. Instead of passing objects by value, objects can be passed by reference. %T. Okay, so pass by reference with an ampersand. Right. So if we pass by reference, then we can make changes to it, but we are changing the original object. The compiler statically guarantees that references always point to valid objects. Okay. Yeah, fair enough. Okay. Cool. Mutability. Mutable data can be mutably borrowed using %mut_t. Mutable reference and gives read-write access to the borrow. In contrast, %t borrows the data via an immutable reference. And the borrow can read the data but not modify it. Right, so if we want to modify it, we need to do the %mut. Okay. A static string is a reference to a string allocated in read-only memory. So that's what that means. %static. Still I don't remember what A meant, but this is useful. Okay, read-only. This function makes reference to a book. So we can edit the book. Immutabook. Create a mutable copy of Immutabook by calling it mutabook. So mut mutabook. Immutably borrow an immutable object. Immutably borrow immutable object. Borrow a mutable object as mutable. Cannot borrow an immutable object as mutable. Okay. So this so does that mean that these are no longer static, author and title? But you declared them in the structure definition to be static. Yet I'm able to modify them? I don't understand. Right. I'm going to borrow this. All right, let's grab this. Because what I want to know is if I do this and then I do this and yeah, do that. Right, and I'm need to put an ampersand here. Otherwise this won't compile for me. Ampersand. Oh no, wrong place. Ampersand there. No, I don't need an ampersand here. Okay. Immutabook. And then what's this? If this is intentional, is what intentional? Unused variable. Variable does not need to be mutable. Oh, okay, well, you know what? Mutabook dot Unknown word. Okay, so it's complaining about the spelling. We can live with that for now. So I'm going to set the breakpoint here because what I want to know is what's the data type of. Right, so let's run this. I want to know what the data type is because the other one was static, right? The rain. Oh, why didn't we get to there? Alright. Let's, oh, because it said, oh, this has no effect. Oh, I think I'm going to need the colon question mark here. And let's put the breakpoint there. Alright. So, run that. Ooh. What's the error? Oh, derived debug. I'm missing a derived debug on book. Okay. And run. Why? Oh, that's why I'm not hitting breakpoints. I'm running. Okay. But it did change it. It's now Fred. Debug. Run and debug. Okay. There we go. Yeah. Would you like to generate? Yes. Okay. Close that because we're good now. Okay. So we got there. Now, if I hover over Immutabook, it says author title. Okay. Author. Immutabook. It roster data pointer. All right. Length 18. So roster blah blah blah. So the read-only thing didn't. It's a compiler thing, the read-only, because when I look at Mutabook from the same point of view, roster, data pointer, length 4, yeah, and it's, so it looks the same. You can't tell at runtime that this said that it was static. So this is a compile time annotation, because that's how that happens. Because if it's a compile time annotation, that makes life easier because you throw it over into a mutable thing, and suddenly the compiler says, "Oh yeah, you can change those," even though the original implementation or the original definition in the structure said that these are static, read only. But this overrides the static, and now it's editable. Okay. All right, that makes sense. It makes life easy, I guess. All right. Mutable. Aliasing. Data can be immutably borrowed any number of times, but while immutably borrowed, the original data can't be mutably borrowed. That makes sense. On the other hand, only one mutable borrow is allowed at a time. The original data can be borrowed again only after the mutable reference has been used for the last time. That makes sense as well. So you can't have two people changing something. So that should be interesting for wonder if you could take advantage of that for asynchronous and multi-threaded stuff, because the other thread, if you owned it, the other thread. But I wonder what happens, because if it throws an exception and craps out on you, then that's not good. Maybe there's some way of taking advantage of that. Yeah, so I think we got this. This kind of makes sense, right? Only one owner at a time. If there is a mutable owner, then only that mutable owner can make changes to it. And multiple. So it's like a database. You can do read locks and write locks. And so, many people can read, but only one writer is allowed at a time. Otherwise, confusion reigns. So that's fine. That's a pretty standard behavior. Like I said, SQL or SQL does that all the time. When doing pattern matching or destructuring via the let binding, the ref keyword can be used to take references to fields of a struct tuple. Sorry. When doing pattern matching or destructuring via the let binding, the ref keyword can be used. Oh, we saw that already. The ref business, this. Yeah, because you're destructuring, that you're pulling out the different properties into separate variables. Cool. And lifetimes. Oy. I thought this was going to be quick, but maybe not. We have lots of different choices of lifetimes. Oh, they're static. Coercion patterns. Maybe. This is where it's actually going to explain the A business. Okay, you know what? Let's stop here for today, and we'll pick up next time with lifetimes. All right, thanks for hanging out, watching this, and I will see you later.